Okay, a quick video on the standard hydrogen electrode. So in using table 24 of the data booklet, we see all these values known as standard electrode potentials. And so we kind of get used to using them, that they give us a value for voltage associated with different half equations. So with different oxidation and reduction for different species. But what are they all based on? So they're all based on the voltage produced, or the cell potential produced, when those different half cells are hooked up to the standard hydrogen electrode. And that's why the value for hydrogen, for its half equation of reduction and oxidation, is listed in the data booklet at 0. So the value for hydrogen's reduction and for its oxidation is 0 volts. And that's because it was chosen as the standard. So going back up, what is a standard hydrogen electrode exactly? A standard hydrogen electrode is an electrode that has a piece of platinum. So there's a wire coming down through here along which electrons can flow, and there's a piece of platinum metal that's sticking down into the solution. So platinum absorbs hydrogen really well and has a porous surface that hydrogen gas can absorb onto, and it's very unreactive itself. So the platinum doesn't actually take part in the reaction, but it acts as a surface upon which the hydrogen or the hydrogen ions can react. But you do need to know that it's made out of platinum. So the hydrogen electrode contains a platinum electrode. It's a solution of hydrogen ions, and the way we do that is we use an acid. Acid gives us a solution of hydrogen ions, and that solution has to be at 1 mole per dm cubed in order for it to be under standard conditions. So 1 molar H plus solution. Now we can get that by doing a 1 molar HCl solution, for example, or we could use a 0.5 molar H2SO4 solution, because every mole of sulfuric acid actually gives us 2 moles of H plus ions in solution. So there's different ways that we can get to that 1 molar H plus solution, but as we've seen from any half cell, it always contains the element and its own ions. And so for hydrogen, we need H plus ions, and in order for it to be standard, we need them at 1 mole per dm cubed. But how do we get the hydrogen in there? So you'll see that you have the metal electrode coming down, and then in this special electrode, it's actually hooked up so that hydrogen gas can be pumped into the electrode and around the electrode at a pressure of 1 atmosphere. And so it needs to be at standard pressure. So for us, in the IB, we would say it has to be at a pressure of 100 kilopascals, which is a tiny bit different than 1 atmosphere, but that's okay. So what's the standard hydrogen electrode? It has to be done at 298 Kelvin or 25 degrees Celsius. You have to have a concentration of 1 mole per dm cubed, and that for a standard hydrogen electrode is a solution of H plus ions or a solution of acid. And the pressure of the gas has to be at 100 kilopascals. So this is a standard hydrogen electrode, a solution of 1 molar acid, 1 molar H plus ions, a platinum electrode, the surface upon which the hydrogen reacts, and hydrogen gas being pumped in at 100 kilopascals. And that acts as the standard. So where do those other values come from? Well, we hook other half cells up to the standard hydrogen electrode and we record the voltage. Now the magnitude of the voltage is one thing. So for example, when you hook up zinc to the hydrogen electrode, the value on the voltmeter is 0.76 volts. But in the table, let me do this one too. When you hook up a copper half cell to the hydrogen electrode, the value is 0.34 volts. So if you hook them up, you can get electrons to flow, and in one of them it says 0.76 volts, and the other one it says 0.34 volts. So how do we decide if it's positive or negative? Because in table 24, the zinc standard electrode potential is negative, whereas the copper standard electrode potential is positive 0.34. And so what that depends on is which direction are the electrons traveling. Are they traveling to the hydrogen electrode, or are they traveling from the hydrogen electrode? So we know from our spontaneous reactions, when we covered this already, that when we have zinc and hydrogen hooked up to one another, we know that the electrons will spontaneously flow from the zinc to the H plus ions. And so the way that it's been defined is that if the electrons flow that way, if the electrons flow to the hydrogen half cell, then the standard electrode potential is negative. That implies that the other half cell, the metal, is a stronger reducing agent and that it will provide electrons to the hydrogen ions and it will reduce the hydrogen ions into hydrogen gas. That's what the negative sign implies. It gives a sense of where is the element in relation to hydrogen on this series. So if it's negative, then that element is more reactive than hydrogen, more active, and a stronger reducing agent. Whereas with the copper, the hydrogen is actually a stronger reducing agent than the copper metal. And so electrons are given down the series spontaneously, as always, to the copper 2 plus ions. So because the hydrogen gives electrons to the copper ions, when you hook up the copper half cell, that potential, that voltage is considered to be positive. So if hydrogen is a stronger reducing agent than the metal or the other species that you've got hooked up, then the potential results being positive. And if what you hook up to the hydrogen electrode is a stronger reducing agent than hydrogen, electrons flow to the hydrogen electrode and it ends up getting a negative potential. And we can see that in these diagrams. In this one, the electrons are flowing this direction from the hydrogen to the copper. So we call that a plus 0.34 volts. And in this one, electrons are flowing from zinc through the voltmeter to the hydrogen, and therefore we call this minus 0.76 volts. So the minus or the plus just has to do with the direction of the electron flowing. Negative means they flow to the hydrogen electrode, and positive means they flow from the hydrogen electrode. That's really not very important for you to be able to explain. You do need to be able to describe the aspects of the standard hydrogen electrode, the pressure of the hydrogen, concentration of the H+, the temperature, and the platinum electrode. And you need to be able to use this table, which I think at this point you already have practice using this table, picking out half equations and determining overall cell potential. So knowing why these become negative versus these become positive in relation to the hydrogen electrode is really not a very important concept to come away with for the IB anyways. So don't stress about that, but that's just to give you some background on where those values come from. Mostly from this video, what you need to take away is what the standard hydrogen electrode is.